Presentation of Science Trek on Idaho Public Television is made possible through the generous support of the Laura Moore Cunningham Foundation, committed to fulfilling the Moore family legacy of building the great state of Idaho.
Anything that takes up space and has weight is called matter. And matter can be found in different states: solid, liquid, gas, or plasma. Want to know more? We're here to answer your questions about states of matter. Science Trek is next. Hi, I'm Joan Cartan Hansen, and welcome to Science Trek, and welcome to the College of Idaho's Physics Lab. We're here to answer your questions about states of matter. But before we do, let's learn a little bit more. Anything that takes up space and has weight is called matter.
When we say anything, we really mean it. Your favorite food is matter.
Your bike is matter. Even your school is loaded with matter.
Matter can be as small as the tiniest cell in your skin, or as large as the whole galaxy. Matter is made of atoms. Matter has mass or weight. Matter can also change from one form to another. The study of matter and the changes it goes through is called physics. Matter comes in four basic states or phases: a solid, a liquid, a gas, or plasma. There are other forms of matter, for example, one called Bose-Einstein condensates. But these exotic forms of matter exist only in laboratories and aren't found naturally on Earth. So let's first talk about solids.
Solids happen when the atoms of matter are densely packed.
Just look around your house. Can you spot a solid? Something that won't change its shape when you touch it. Your bike or a computer are both good examples of a solid.
How about the next state, liquid? Water, milk, and juice are all good examples.
In a liquid, the atoms aren't as closely packed, and the matter takes on the shape of what's around it, like water in a glass. Next, there are gases. The atoms in gases are spread out and bouncy.
Gases are usually invisible and have no shape. Unlike a liquid, you cannot spill it, and unlike a solid, you cannot touch it.
A gas, like air, is easiest to see when we fill up a balloon or watch the wind blow. And then there's plasma.
It can be kind of tricky to spot if there's a fluorescent light in your house. If there is, then you found plasma. The light it makes is glowing plasma.
You also see plasma when you look at the stars. Stars are big balls of gases at really high temperatures, and high temperatures charge up the atoms and create plasma. Temperature is one of those physical forces that can change matter from one form or phase to another. By changing the temperature, either hot or cold, you have added or subtracted energy. You've made a physical change in the matter. But even if the matter takes a different form, its chemical makeup doesn't change.
Take water, for instance. It's made of 2 hydrogen, 1 oxygen, and if you heat it, it turns to steam. If you freeze it, it turns to ice. But what doesn't change is what it's made of. It's still water.
The physical state of matter, whether it's a solid, a liquid, a gas, or plasma, is a description of the state of its atoms. Matter is large and matter is small. It has mass or weight, and it can change its form.
It's basically all the stuff around you, no matter its state.
And joining me now to answer your questions about states of matter are Catherine Devine, Assistant Professor of Physics at the College of Idaho, and Christopher Saunders, Visiting Professor of Chemistry, also from the College of Idaho. Thank you both for joining me. I appreciate it.
Thank you, Joan. It's really nice to be here.
Yeah, thank you for having us.
Okay, let's go to your questions.
Hi, my name is Justin from St. Damien Elementary, and I would like to know how is a solid made?
So a solid, it depends on what you're starting off with. So if a material is already in its solid phase, you already have the solid and you don't need to necessarily make it. But let's say you want to take something like liquid water and you want solid water, which we call ice. You would need to cool that down until you reach its freezing point. Another way to do that, though, is also by changing the pressure. So pressure and temperature both have something to do with changing the phase of something. So changing something from a gas to a liquid, or, as you asked, a liquid into a solid.
Katie asks, who found out about matter?
Well, matter existed long before humans did. So every human that's ever been around kind of knew about matter in the sense that there were things there and they were solid or liquid or gas. But it was a Greek philosopher by the name of Empedocles from about 400 BCE that was credited with kind of giving things different classifications. So he had earth, air, water, and fire. And then Chris, did you have?
Right, so then after that, it was another Greek philosopher called Democritus who came up with this idea that matter, if you keep cutting into smaller and smaller and smaller pieces, you eventually come up to a particle that you can't cut into anymore, and that was the birth of the idea of the atom. Unfortunately, that idea wasn't believed by some of the big philosophers at the time, including Aristotle and Plato, and it wasn't until 2,000 years later that modern scientists and the birth of modern chemistry came into play and now shapes our current understanding of what matter is and how we classify it.
Hi, my name is Brandon. I go to White Pine Elementary, and the question is, how many gases are there?
So good question. The easy answer is a lot. So in theory, most every compound that we can think of could, in theory, under the right conditions, the right temperature, the right pressure, could exist as a gas. So pretty much all different types of matter could be a gas. So again, everything could be a gas.
Hello, my name is James. I go to West Junior High, and my question is, can a metal transform into a state of gas?
Absolutely. I think one of the examples that people hear about a lot is the metal, what people consider the metal mercury, which most people, when they think of mercury, think of it in its liquid form. But mercury evaporates at air temperature, and so mercury gas is one of the things you kind of have to watch out for because that's actually pretty bad for you to breathe. But that's one that I think of pretty commonly. But any metal essentially can become a gas form if it's at the right temperature and pressure.
Hi, my name is Cynthia from Cynthia Mann Elementary, and my question is, why will Alka-Seltzer bubble up like a lava lamp when you put it in oil and water?
Well, I'd never actually heard of this experiment before, so we decided to just give it a shot. And we'll just be scientists here and describe to you what we see happening. So first, let's do the oil and water.
So we have some regular vegetable oil, and we have some water. And so we're going to pour the oil into the container. So already you can notice that the two do not mix, and you might already know that because you might have seen this at home. So the different chemical properties of that oil and water make it so they don't like to mix with one another.
But they're still both liquid. The reason the water sits lower than the oil is because of density, and so the water has more mass per little unit volume, and so it sinks basically compared to the oil. So the oil is resting on top and the water's on the bottom.
Okay, so let's put our Alka-Seltzer in there and observe.
We'll see what happens.
So already I'm trying to imagine what I think might happen. So maybe you at home might want to think, what do you think is going to happen? Is it really going to look like a lava lamp? Okay,
ready?
Put it in there. Okay, so already I could see some of those globs that look like a lava lamp. I think that's from the oil that picked up when the Alka-Seltzer fell through that. But now it's really bubbling, so we have a gas, so we have another phase of matter.
So the Alka-Seltzer, when you drop it in the water, there's a chemical reaction that produces a gas. And the gas has even less density than the water or the oil, so it bubbles up to the top.
So now if you can see, there's some large bubbles that are forming inside of the oil. So the gas is being produced down here as tiny little bubbles, and when it gets into this oil, it likes to stick together, and so the oil then is moving around kind of like a lava lamp as the question asked, because again, the water and the oil don't want to mix together, but the gas is pushing it all around, causing that turbulence. And now it's so full of bubbles, it's hard to see anything.
Another property of liquids that this kind of demonstrates pretty well is the idea of viscosity, that oil, that kind of stretchiness and sticking togetherness and the slowness to move through, is scientists call that the viscosity of the liquid.
Water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, but salt water freezes at a lower temperature. That's because the salt sort of gets in the way of the water molecules forming ice. So different substances have different freezing points.
Hi, my name is Katie, and I go to South Middle School. And my question is, what is the fifth state of matter?
So the fifth state of matter people often use to refer to Bose-Einstein condensates. And so the three states of matter that we most often learn about are solids, liquids, and gas. And then plasma is the fourth state of matter. And then Bose-Einstein condensates are what people commonly refer to as the fifth state. And they're subatomic particles at near absolute zero, and they have really interesting properties.
Cam asks, can you turn air into water?
Air in this room has a lot of different types of gases in it. There's nitrogen gas, there's oxygen gas, there's water gas, so some of the big primary players. And so right now there's gas in this room, or there's water in this room in its gas state. And so in order to turn air into water, what you would really be doing is condensing just the water molecules into waters in its liquid form. If you really were messing with the conditions of the temperature and pressure of the room, you could probably get the oxygen and nitrogen to take its liquid form as well. But since air is made up of so many different types of gas, you would take all of those into their different liquid forms.
And a quick experiment that you can do to do that, to see the water that exists in air is simply get close to a mirror and breathe onto the mirror, right? And you'll fog up that mirror. Well, that fog that you see on that mirror are tiny little droplets of water that has condensed from the water that already exists in the breath that comes out of your lungs.
Hi, my name is Maddie, and I go to Horseshoe Bend Elementary. And my question is, would the states of matter be different on another planet?
No, actually, the states of matter would be the same no matter where you were in the universe. One of the kind of neat things about physics and chemistry is that the laws about physics and chemistry are the same on Earth as they are anywhere in the universe. And so the idea of phase changes and what molecules are out there and how atoms behave is the same, we assume is the same everywhere in the whole universe.
Hi, my name is Caden from Cynthia Mann Elementary School, and my question is, why can't you see most gases?
Most gases are invisible. Most of the gases aren't detectable with the eye. There are a few gases out there that you can see with your eye, but unfortunately, most of those visible gases are highly toxic.
And that's not to say a lot of the invisible gases as well can be toxic. So just because you can't see it doesn't mean it's not there, and doesn't mean that it can have an impact on you. You know, as you're driving, right? As you're driving in a car and you put your hand out the window, you feel that air, right? You can't see it, but you can certainly feel it.
My name is Ethan. I go to North Star Charter School, and my question is, how does baking soda and vinegar react?
Okay, Ethan, well, the best way to talk about this is to show you and talk about what's happening. So here we have a little bit of baking soda. This is the same baking soda that you probably have in your kitchen. And I'm just gonna put a little bit in the speaker here. And then
here's some vinegar, probably same vinegar you have in your kitchen. Shall I add it?
Yep.
All right, here we go.
Okay, so what's happening is a chemical reaction. We know a chemical reaction is taking place because we can physically see something happening. So vinegar and baking soda are two very good examples of classes of compounds that we call acids and bases. So the vinegar is primarily made out of acetic acid, and the baking soda is a base. So when you mix those two things together, you get an acid-base reaction. And in this case, one of the products of that acid-base reaction is the production of carbon dioxide gas. So that's what was making the bubbles. It's an invisible gas. We made it, but we can't see it up here. But it's the same carbon dioxide gas that makes your Mountain Dew fizzy. So those little bubbles are carbon dioxide gas, the same gas that we produced in this chemical reaction.
We've come upstairs to the College of Idaho's chemistry lab for a few more experiments. Chris, I'm going to put my safety glasses on, and you take it away.
All right, thanks, Joan. So what we have here are some simple demonstrations of, one, a chemical reaction, and also different phases and some phase changes. So you see here that we're using a Bunsen burner. So a Bunsen burner works off of natural gas. So we have a gas coming out here. Now I'm using that flame as a source of heat. So this flame now has heated up this liquid water that we have in the bottom of this flask, and you can see that it's bubbling and that it's boiling. So as that water boils, it turns into the gaseous form of water. Now if you look really closely, you can't see that. Okay, so water vapor is an invisible gas, but if you follow the route that gas will take, it comes up the column. You can see little droplets of water on the side. That's from the water condensing back into its liquid form. Now if you again follow it down out of this small tube, you can see that jet of steam coming out of the side. Now again, that's because the gas pressure is building up and it's pushing all of that gaseous water out. What you see in the form of steam is, again, it's not the gas. It is the condensing water vapor of, again, the gaseous water turning back into liquid water. And that's what we refer to as steam. Okay, so what I'm going to show you is a chemical reaction between two things. So I have some copper wire, and we have some nitric acid. And when we mix these two things together, we form a gas. In this case, the gas is nitrogen dioxide. Now you'll be able to see the gas. This is not an invisible gas. This is a very visible gas. You will see a brown cloud of smoke come out of this. It's a very toxic gas, and that's why we're doing this under a chemical fume hood. So you notice a number of different things happened. So there was some fizzing, some bubbling. Again, that gas that was produced, as you can see here, is the nitrogen dioxide gas. If you can look closely at that, you probably won't see any bits of the copper wire anymore. They are now in solution. That's why the solution changed color to that kind of that greenish blue color. So solutions that have dissolved copper ions in them typically turn that blue green color. But again, this demonstrates a way to make a gas using a chemical reaction, and to show you that not all gases are invisible. We can actually see some of those gases. And a good rule of thumb is that if you can see a gas, so if a gas has a color to it, then it is most likely toxic, and you should probably not inhale the gas. That's not to say that there aren't invisible gases that are toxic, but again, if you can see the gas, you should not inhale it. You notice less and less gas is being produced. The reactants for this reaction are finally running out, and once we use up all of it, no more gas will be formed and the reaction will be complete. So what I have here is a sample of liquid nitrogen. So nitrogen usually is a gas. So right now you're inhaling large amounts of nitrogen. Now when you get nitrogen really cold, it turns into a liquid. And you can see the liquid in here. Now, liquid nitrogen boils at a very, very low temperature. It's still boiling, but it's very, very cold. So cold that it would hurt my hands if I had on there. So I'm wearing safety gloves. So if I pour a little bit of this out, you can see that the little drops of it instantly boil, and you can see again the condensed water vapor from that cold liquid nitrogen that's now turned into a gas. So let's do that again because
it's fun.
Because it's fun.
Another fun experiment you can do with liquid nitrogen involves freezing things. And so most living things are primarily actually in a liquid state. You may not think about yourself being a liquid, but think about all the blood and all the water that you're made of. We're mostly water, and so are flowers. So if we take a flower and dip it into the liquid nitrogen will cause all of the liquids in the flower to undergo a phase change and become solid.
Now, so you may have noticed a lot of vapor came out of it right away. That's because the heat from that flower that was a little bit warmer helped boil some of the liquid nitrogen right away as we put it in there. So let's wait a few seconds and make sure that we get it nice and frozen. Now all of the liquid that was in here should be frozen, and now it becomes very brittle. And instead of being that flexible liquid portion, it's now can be broken into little pieces.
So now we're going to do a demonstration showing how you can tell if an invisible gas is present. So right now I have a beaker. It's empty. There's nothing but air in it. And I have a balloon that I'm going to fill up with air. And make sure it still fits in my beaker. And since there's nothing but air in my balloon and nothing but air in my beaker, and the balloon has a little bit of extra weight from the rubber. If I drop it, it will float down to the bottom of the beaker.
And now we can fill this beaker up with sulfur hexafluoride, which is a very dense gas. Now we won't be able to see it, but in a little bit we'll be able to tell that it's there.
Now if I place the balloon in the container, it doesn't sink because it's floating in the very dense sulfur hexafluoride. So even though you can't see that the gas is there, the balloon no longer sinks because we've got that invisible layer of sulfur hexafluoride supporting the balloon, so the balloon doesn't sink. And just to prove to you that we didn't do anything tricky, if we pour out the invisible gas, empty our container, and drop the balloon again, it will sink down to the bottom because there's no longer any invisible gas in there to support it.
This was great, thank you. Okay, we're gonna go back downstairs and answer more questions. Katie asks, why is matter important?
Why is matter important? Well, think about where we would be without matter. We wouldn't be without matter. We're made of matter. And so all of the liquid you drink, all of the stuff you're made out of, that's matter. And so I think matter is pretty important to me just because I like to exist and I like to be made of matter.
Well, and if there was no matter, then I wouldn't have a job. So the study of matter is what we call chemistry. And I like to tell my students oftentimes that chemistry is the study of the familiar because matter is all around you. You're made of matter, right? You're touching matter all the time. You can't get away from it. So if you're right, if anything is important to you, then matter is important because it's made out of matter.
Hi, my name is Ryan, and I go to Cynthia Mann Elementary School. My question is, does dry ice burn your skin, and why?
I don't know, let's see.
Oh wait, Chris, no, don't touch it. You need gloves to touch dry ice safely.
Kitty's definitely right. So when you say burn, we often think of heat. And heat and damage aren't necessarily the same thing. So yes, very hot things can hurt our tissue, but also very cold things. So in this case, dry ice is solid carbon dioxide. So this is a piece of dry ice. So this is made out of the same stuff as the carbon dioxide that's in the air that you breathe, in your Mountain Dew, any sort of carbonated beverage. And it is very, very cold. So we have to get it really cold to turn it into a solid. It's so cold that if I wasn't wearing these gloves and I was hanging on to this long enough, it would burn my skin in the sense that it would freeze my tissue and cause the cells in my hand to start to die, and it would hurt. It would not be very pleasant. So I'm wearing gloves and being safe when handling the dry ice.
So, Chris, since we've got this bowl of dry ice here and I've got a glass of water, should we do kind of a fun demonstration?
Absolutely.
Okay. So, what you can probably see here is that when you pour water on dry ice, you're able to see this thing that looks like a cloud form in the bowl. And what's happening, if you can see down in there, is you might see bubbles coming up from the inside too. And the carbon dioxide that we had as a solid form is now boiling off and forming carbon dioxide gas. But carbon dioxide gas is invisible. So what are we actually seeing, Chris?
So what we're seeing, what Katie called boiling is actually in the case of carbon dioxide, it's something that we called sublimation. So the carbon dioxide starts off as a solid and it completely skips the liquid phase and it goes into a gas phase. So that's called sublimation. So it's bubbling because the gas is coming off of the solid carbon dioxide. Now why it started to bubble more when she added the water was the fact that the water had a certain amount of thermal energy in it and is now being transformed, it's being transferred into the dry ice, turning it into the gaseous form. Now, what you asked about in terms of what we're seeing is very important. So most people would say, oh, I can see the carbon dioxide gas, right? There's this gas, it's coming out, right? We can blow it around and it's floating. What you're actually seeing is liquid water that has condensed from its gas form into its liquid form. Why is it condensing? Well, it's condensing because that carbon dioxide that's coming off of here is very cold. And so as that carbon dioxide comes off, liquid water the gaseous water that's already in the air condenses down. So what you're seeing technically is condensed water vapor.
So this is actually a demonstration of two phase changes then. We've got sublimation, where the carbon dioxide is going from solid to gas form, and then condensation, where the water vapor is going from gas to liquid form.
Correct. And you notice too that the vapor kind of sits down. It's very dense. It's heavier than the rest of the air. And that's because the carbon dioxide is more dense than what's around it. So you see the gaseous water condensing into liquid water, and it follows where that carbon dioxide goes.
Catherine, before we run out of time, let me ask, why did you pick a job in physics?
So when I was in college, I knew I liked science, but I didn't know exactly what kind of science I wanted to study. And when I took physics, I took it early in my college career because physics is really, really helpful to all of the other sciences, whether you want to study chemistry, biology, medicine. If you want to go into science, you really should take physics. And then I just realized I really liked it. So I kept taking physics, and then I started teaching physics, and I've never really left.
And Christopher, if someone is interested in a job in physics or chemistry, what should he or she study in school?
Well, I think beyond, taking as many chemistry and physics class or biology classes or other science classes that you can, is to remember that math is a very fundamental part of science, of scientific calculations, and that should definitely be a part of what you study in school. And my other piece of advice is to make sure that you remember that it's fun and that it should be fun and that science is interesting. We're always discovering new things. And yes, sometimes it's challenging, but it can be very, very rewarding.
One of the things people don't really maybe often realize that our job as scientists requires us to use is we also have to write pretty well, and we have to communicate clearly. And so just because you're taking all these math and science courses doesn't mean you shouldn't be good at the other stuff. And so learning to write well, communicate well, all of that is really important for getting a career in science.
I'm sorry, we've run out of time. Thank you both for answering students' questions.
Thank you for having us. This was a lot of fun.
Thank you. It was a pleasure to be here.
And our thanks also to the folks here at the College of Idaho's Physics and Chemistry departments for hosting us. Do you have a question for future shows? You can email it or send it as a video question, recorded on your cell phone, tablet, or webcam. Or if you're an educator, we'll even lend you a camera. And if you send in a question, you and your class can win prizes. Our last prize winner was Gunnar in Mrs. Edwards' class at Liberty Charter School in Nampa. So to find out about today's topic, go to the States of Matter section of the Science Trek website for facts, links, lesson plans, and more. Or watch Science Trek, the web show. So send in your questions, and each week, check out my blog for the latest science news for kids. You'll find it all at idahoptv.org/Science Trek. We'll see you next time here on Science Trek.
Presentation of Science Trek on Idaho Public Television is made possible through the generous support of the Laura Moore Cunningham Foundation, committed to fulfilling the Moore family legacy of building the great state of Idaho.
If you want to learn more about this topic or watch our videos, check out the Science Trek website at idahoptv.org/Science Trek.